In this lesson, we are going to be covering random forest. This is going to be a class on random forest. In the last class, we looked at decision trees, and today we are going to be looking at random forests. And like decision trees, random forest also has um, classifier and regressor. And like we always do, we are firstly going to understand the idea behind it, how it works under the hood. Then we are just going to quickly write almost the same kind of code I've been writing, just to like see how to implement it in Sklearn. Sklearn, like you've seen over and over, is a very beautiful and powerful Python library for implementing majority of data science concepts on our own data set. So now, without further ado, let's get into it. So what's random forest? So random forest is a technique um, called bagging. It's an assemble technique. Assemble as in ensemble, like this ensemble. It's an ensemble technique, and it uses something called bootstrapping. In random forest, we do two things called bootstrapping plus aggregation, and that's the whole idea behind it. In fact, in this particular one, you're not going to be seeing um, any math really, because random forest is just like a way of making decision trees like a lot better. Now, so what are actually the problem with decision tree? So the first problem with decision tree is that decision tree actually, especially very deep decision trees, suffers from something called high variance, right? High variance. And if you don't already know, variance, there are actually two important concepts in machine learning generally, which is bias and variance. So, what is variance? You can think of variance as the degree of change, or how much a model changes, or the prediction of the model changes when the training data, when it changes a little bit. And it is not like you have a training data that is like out of distribution, just like within the same distribution, like training data within the same distribution. If you train your data, if you train your model with some kind of data and the model learns very well, then you just like tweak the data a little bit without going outside of the distribution of the data set, and you see that the model begins to suffer, like the model cannot really predict. So you can say that the model has high variance, and usually high variance means overfitting. That is, the model has actually like um learned majority of the noise that is in the data set, and it cannot really generalize very well, right? And bias. So bias is the ability for the model to actually generalize, and that's low bias. Like a model having low bias means the model can generalize very well. So bias itself actually measures the average difference between model prediction and the true value, right? So high bias will mean like there is high difference, there is a very large difference between the average prediction and the true value of the model, and the true value of the data set. Meanwhile, low bias means the difference between the model prediction and the true value is very small. So we want essentially we want a model that has low variance and low bias. Low variance meaning if we change some of the data, that is, if our model should see some new data that is still within the distribution of what we trained it on, it is still going to perform very well. That is, it has not overfitted so much on the instances that we train it on. That's low variance. What's now low bias? Low bias means if we should compute the difference, that is, if we should try and measure the difference between the model output and the true value, it is going to be small. So usually a very good model, an exceptional model, is a model that has low variance and low bias. And if you have a model that has high variance and low bias, it means that that model has overfitted. That is, small change in the training data leads the model to perform badly, even though it has low bias. That is, even though on its current prediction, on its current performance, we can see that it fits. That is, the difference between what is predicting and the true value, they are not too much, right? So I hope you get the whole idea of bias and variance. Now, for decision trees, especially deep decision trees, they have high variance, right? Meaning that if we have a split, let's say we have a split like so, and the split goes like this, let's say like this, something like this. Now, it means that let's say here we have x less than or equals to 5. Let's say x less than or equals to 5, we have this. Then maybe here we have x greater than or equals to 15. And that's what took us like this. Right. Everything that happens here, all of this stuff depends so much on this particular split. That is the reason why we observed this and this and this. The, the reason is not because this all of these things are the best way to go. That is because, well, we've already headed this direction, which at the time of going this direction, if you know how decision trees work, at the time of going through this direction, this was the best way for us to go, right? Because the model recursively computes all of the information gains and look for the split that actually gives us the information gain, the maximum information gain at this point. But the moment we move past this point, well, everything that we're going to be seeing that depends on this point. So we don't know whether if we had changed this to x greater than 3, at this point, it would not have been the best way to go. But we don't know whether after that point, what is going to be a for x greater than 3, for example, is going to be better than what we had here. You can think of it as you are going, you got to a junction and you went left. Everything that you're going to be seeing moving on is going to be because you went left. So you are never going to find out if there are some better things to see ahead if you had gone right. So that means that if we change anything in the training data, the decision tree is going to suffer a lot because it is heavily dependent on what is inside the data that we train it on. And that is what random forest comes in to fix. So what happens with random forest? So what happens with random forest is the step is basically very simple. The first thing that it does is, let's say we have some data x1, x2, let's say x3, and we are trying to predict y. Let's say it like this. So what happens is, I'm not going to be filling it up because it's really easy to understand. So the first thing that we do is we choose something called n estimators, and n estimators is basically the number of decision trees that we want to train. So random forest is just basically a combination of decision trees. And from the name, one tree makes um one tree. Then if you have collection of trees, that would mean you have a forest, right? Great. So if I say n estimators equals 5, it means that I want to train a decision tree, a random forest model that has 5 different decision trees inside it. So how is this going to happen? The first thing that happens is something called bootstrapping. So we are going to bootstrap. And what happens when we bootstrap? So let's say this is our row one. Let's say row one, row two, row three, row four. Let's say something like that. Great. So the first thing that happens is we are going to bootstrapping is we randomly sample units of out of our data set. That is, we randomly select some of our data sets, and it is going to be a simple random sampling with replacement. That is, the fact that we can have our first, let's call it n, and say n1 can be r1, r2, r1 again. So let me show it to you. So this, we are saying take row 1, row 2, and row 1 again. We are going to fit a decision tree on this. Let's call it dt1. So we're going to fit a decision tree on this, get our output, and it is also not going to be on the entire columns. We could fit this on just x1 and x3. Then we can select R2, R3, R1 again and fit that, call that, excuse me, we can call that decision tree. We can train decision tree 2. So like that, like that, like that, we keep selecting. And at the end of the day, we are going to have 5 decision trees. First one trained on not the entire data set, but just a subset of the data set. Decision tree 2 also is going to be a subset of the data set. Decision tree 3 is also going to be a subset of the data set. So our n estimator is 5. So we are going to have 5 subsets of the data set, and we are going to train 5 decision trees on them. And when we are done, if we are working on a classification problem, we are going to take a majority vote. So we're going to take a majority vote. Let's say decision tree 1 says the answer is yes, 2 says the answer is yes, 3 says no, 4 says yes, 5 says yes. We know, okay, majority of people says yes, so that means the answer is yes. And if it is a classification, if it is a regression problem, we are just going to average, we'll compute the average. So we compute whatever the average is for each of the trees, and that's what gives us our answer. Now, what does this ensure? The only, like, the biggest upgrade that random forest provide over decision tree is that random forest is going to really, really deal with the problem of high variance, right? It is going to reduce the variance because now you are not training on the entire data set at once. You are training several small, small decision trees on independent samples of data set. That is, what decision tree one sees to make its prediction is not entirely what tree two sees. It might not even, like, they can be completely different what is in terms of the records. So it reduces variance. That is, the problem of high variance that exists inside decision tree is not something that you're going to find um inside random forest. Now, another thing is, although this thing where we reduce variance, it does not affect the bias. Don't forget that I said earlier that decision tree can overfit, and overfitting is basically high variance, low bias, right? But in random forest, bias does not get affected because if you have think about it, if you have a very deep tree, at least if you have one deep tree that has low bias, if you train 5 different trees to make up a random forest and each of them has bias, averaging it out or taking majority vote is not going to impact the bias um that is inside the each of the trees. So that is the reason why bias does not get increased. The only thing that gets impacted is the variance, right? Yeah, so that's just the core idea. And this part where we do majority voting and, or averaging, is what we call the aggregation part. And that's why this thing is called bagging. So bootstrapping is where we select the part of the data sets that we want to use. We randomly sample, that is bootstrapping, and then we train on it, then we do averaging, which is the bagging part. So that is entirely what random forest is, from just the intuition aspect of it. So, and if you understand everything that I've been saying, you're going to know that all of the hyperparameters of decision trees are, you can carry them over into random forest. Then with one extra parameter, which is n estimator, this one here, n estimators. So n estimators is that one extra parameter that you are going to find inside random forest. So let's go into this place and write a random forest regressor. We're going to import pandas as PD. Let's run that to activate collab. So we're going to say from sklearn dot ensemble. So uh This assemble is where you are going to have random forest. So random forest regressor, and we can see from Sklearn dot pre-processing and import um, label encoder, and also import standard scalar. So from sklearn dot matrix, we need to import root mean squared error because this is going to be a regression task. And lastly, we're going to say from sklearn dot model selection, we're going to import train test split, and I'm going to say import plotly because let's use the plotly.express as px. So we are going to be using the practice dataset, that tips dataset from plotly, just to quickly model or something. Tips, I'm going to say data.ed, and that is going to give us this, yeah. So like this, so these are data set, and what we just want to predict, we want to try and build a model that can predict tips, like the tips that people are going to pay. You can think of this as a restaurant setting. So yeah, let's get into it. Let's just split our x and our y. So I'm only going to be doing the pre-processing, the cleaning that takes us to building the model. Like I always mention in every single video, you should do a lot of data handling, you should do a lot of data visualization. Nobody jumps into just building model. That's recipe for disaster. But this particular series is just focused on showing you how models are trained. So that is it, right? So you should always clean. The only reason why we're not doing extensive cleaning is because there's another playlist that focuses on exploratory data analysis. So yeah, let's move on. And we're going to say x equals data, and we are going to be doing the drop, and we are going to be dropping what are we going to be dropping? We're going to be dropping tip, and our y is going to be equals to data of tip. Perfect. So another thing that we can do is let's just run that. So the next thing I'm going to do is convert all of these categorical variables, encode them, then scale the whole thing, and we can move to what matters. So we're going to encode the categorical variables and then scale, scale, then scale. Yeah, that's perfect. The data set. So we're going to say that categorical columns equals x dot select the types. We're going to include, excuse me, Control Z, Control Z. We're going to include only objects, things that are of the type of the object. I'm going to say dot columns, and if you check out what cat codes looks like now, this is it, a smoker daytime. Then we can loop over that. So we can say for column in cat codes, that is in categorical columns, we're going to initialize our encoder and say encoder equals label encoder. Then we are going to say encoder x of column is going to be equals to encoder dot fit. You've seen this before, I'm sure. You know, we do encoder dot fit transform, and we do x of column, which is the column that I want to fit. And if you are fine with, I used to say label encoder is not something especially fancy. You can do it manually if you want. Really, it's just calling some list comprehension on a data point. If you want to do it by yourself, fine. Then you probably need to set up another dictionary that you can use to track the kind of encoding that you've done. It's just basically if dinner, if this row, if the entry in time column is dinner, call it one. If it is lunch, call it two. So encoder is not something fancy. So after that, we just run this. So we should check our x now, x dot head. We see that everything has been encoded. So the next thing we are going to do is scale our data set and split first before scaling. And this is extremely important. You don't want to scale before splitting so that you don't leak information in the training data into the test. So we're going to split and scale the data set. So how do we do that? We are going to say x underscore train, x underscore test, y underscore train, y underscore test. That is going to be equals to train, test split, x comma y, test size equals 0.15 random state for reproducibility equals 23. And after that we can scale, so we can say x underscore train, we can say columns equals x underscore train dot columns. That is if I want to, but there's no point. I don't want it to be a pandas data frame at the end of the day. So we can just scale. Say scalar equals standard scalar, right? And we're going to say x underscore train equals scalar dot fit underscore transform x train. Then we can do x test equals scalar dot transform x test. Perfect. So we can go ahead and train our model, which is the same flow that you've seen time and time again. And say model equals random forest regressor. And we're just going to pass random state. It has a lot of hyperparameters. Can you see them? N estimators, criterion, max depth, N estimators, then basically every other um hyperparameters that you find in a decision tree. But don't worry about hyperparameters yet. There is a class on hyperparameter tuning that we are going to be extensively going into majority of these hyperparameters and how to combine them, how to choose the best set that result in a perfect output. But for now, just random state for reproducibility. Then we're going to the model of fit x underscore train, comma y underscore train. Then we can see train pred, we get predictions equals model dot predict x underscore train, and test preds going to be equals to model dot predict x underscore test. And that is done. So the next thing is you want to evaluate the model performance, see how our model did. It is definitely going to overfit because random forest, I'm just suspecting random forest is probably going to be too complex for this. We have to tune it, but that's not the problem that we need to worry about right now. So we say train RMSC, that's going to be equals to root mean squared error of y train, comma train pret, perfect. And second one is going to be print f string test RMSC, and that is going to take us to what again? This the same thing, root mean squared error y underscore test and test underscore pret. And if we run that, we have our output, and we see that the model has overfitted. And why are we saying the model has overfitted? The reason why we are saying the model has overfitted is because um, the output of the train is lower than test. And don't forget, regression is a minimization problem. Regression is a minimization problem. So yeah, that is that. So this is the way you are gonna you train a random forest regressor. Very easy. The same thing that we've been doing before, nothing changes. In fact, the key takeaway from this session and majority of it is just the understanding of the idea that we explained in here, right? So yeah, that is that on random forests, and I'm gonna see you in the next one. Have a great day.